Let's start by demonstrating the first stage, which is the pre-processing stage. So I'm going to open a new C file for this. Let's call it main.c. I'm going to define a macro over here. Let's call it cat. And it's going to be defined as meow. Now I'm going to write here cat a couple of times to see how the preprocessor affects this. So I'm going to write it like this, I'm going to write it like this, and like this. Now let's save this and compile this with GCC. Except I'm going to tell GCC to stop at the pre-processing stage. And for this we can use a special flag, so I'm going to open the info page for GCC. Generally when you use GNU utilities, it's better to use the info pages, they're more rich than the man pages. And here I'm going to scroll down to invoking GCC. And then scroll down till you get to overall options. I'm going to enter this one. Now just scroll down till you get to this section over here, if you want only some of the stages of compilation. Let's take a look at the different options we have here. We can use this option over here to stop after the pre-processing stage. So let's use this. So I'm going to run gcc-e and then main.c. Let's run it over here. And here you can see the result from the pre-processing stage. The cat and cat here has been replaced with meow. When it's connected, it's not replaced, which is expected. And finally, the last one was replaced as well. Now let's move on into the next stage, which is compilation. And this time I'm going to write a valid C program. So I'm going to delete this, and let's just make a main function over here. And what I'm going to do to make things more interesting is I'm going to reference a function that is not in this file. So I'm going to call this function foo. And I'm going to call it from main. Now let's save this. And this time I'm going to use the -c option to compile only. So it's going to be gcc-c, then main.c. Now if you take a look at ls over here, you should have an object file like this. This file is still not an executable, but this can be used by the linker to create the executable. If we try linking this with ld, so I'm going to link this. Okay, as you can see, the linker found two issues. First of all, it can't find the entry point of the program. It's expecting something that is called _start. Now, we are used to, as C programmers, to call our first function main. But really, this is not the first function that is running. This is the default name of the function that libc calls, after it does its own initialization. The convention of the real entry point of programs is _start. And we're not going to use libc in this video. So I'm going to rename my entry point as _start. So it's not going to be an int function anymore, it's going to be a void, then _start. Now if I run the linker again, so I'm going to clean this and run this again. Sorry, I need to compile before. Now run the linker. Okay, now we're left with only one linker error, which is expected. We're referencing a function that we didn't define. It's only declared over here, it's foo. Now let's look deeper into this. How does the linker know that I'm referencing a function called foo? And it tells me exactly where in the code I'm doing this. If I just run file on the object file over here, which I tried to link, and you can see it's an elf file. So it's the same format that is used for executable files on Linux. So what I'm going to do is I'm going to use a utility called readelf. Specifically, I'm going to use the -a option to just get all the information from the elf. So I'm going to run readelf and then -a with main.o. And let's pass this into more because it's going to be a lot of information. Okay, cool. And now we can see a bunch of low-level information about the elf itself. For example, here is the magic. And this is, by the way, elf in ASCII. This is how you can identify an elf with your eyes. But as you can see, this program displays in human-readable form all the binary data that is inside of this elf file. For example, we can see that this is an elf 64, 64 bits. Now I'm going to scroll down by pressing space. And over here you can see the relocation section of .text. .text is, by the way, the binary machine code. So this is the relocation that is related to the machine code of our program. What do we have here? We have foo, which is the missing function. And here you can see that this relocation is happening at offset 5. So let's take a look at what is in offset 5 of the assembly code of this program. So for disassembling the code, I'm going to use objdump. So let's open the man page. And I'm going to use this option over here, disassemble. This will disassemble only the sections that are relevant for code, not the whole binary. So I'm going to run objdump-d and then the object file. Now remember, the offset of the relocation was 5. So you can see here the entry point, the assembly, and here's the offset of each instruction, and this is the machine code of each instruction. This instruction over here has 3 bytes and starts at offset 1. So you can see the call over here. This is the call to the foo function, which is not resolved yet. So this starts at offset 4. Now the reason we saw the relocation offset as 5 is because the linker is going to want to replace these over here. because this is part of the assembly instruction telling that this is a call. But this is where I'm going to call, the address I'm going to call. Now, if we take a look at the Intel SDM, the instruction manual, in the section that talks about the call procedure, the call instruction, we can see that in our case, it's using this option over here, which is call a relative displacement of 32 bits. And we can see that it starts with an E8, as it does over here, and then a 32-bit address, which is this. So this is going to be the address that the linker is going to fill with the real value of foo. It's currently just a bunch of zeros. Okay, and now let's get this linked successfully by defining foo. So I'm going to open a new file over here and call it foo.c. Okay, and I'm going to compile this. And now if we link the object file of foo together with main.o, now it passes successfully. And if we take a look at the assembly, a default name of the linker is a.out. It's a legacy name for an old format before elf. So I'm going to use the -d for disassemble. Now I can see the start function over here calling foo. And foo is right over here. And then it goes back to start, which returns. Let's try running this program. So I'm going to run a.out. And we get a segmentation fault. Why is that? So I'm going to run a.out with GDB. And I'm going to put a breakpoint on start. So I'm going to use the R command to run the program. Now I'm going to enable the TUI mode. So I'm going to run TUI layout ASM. Now I'm going to use NI for the next instruction. Now we can start seeing the assembly over here. Okay, so we can see that we're now after the call to foo. So let's continue to the next instruction. And now take a look what happens when I return. It goes to the address 1 in memory, which of course is invalid. Now let's see something very interesting. If I run this program with, let's say, 3 arguments, let's see where it's going to jump after the return. I'm going to say yes, start from the beginning. Let's go again to the return instruction. And if I proceed on, now it's at 4, not 1. So what you can understand for this is that Linux puts the arguments on the stack. Now, since I'm now the actual entry point of the program, I'm not going through libc anymore. Libc is not calling main for me. I am the real entry point. So returning is not good because there's nowhere to return. What I need to do instead is, of course, properly exit the process myself. But if I want to keep my program from crashing, I'm just going to quickly make an infinite loop. So I'm going to go here to main and then just create an infinite loop here. This will just keep the program from crashing. Now let's save this, compile main, and link everything together. Now if I run a.out, it's not crashing anymore. Let's take a look at the size in the disk. Okay, yeah, so it's 9K. Just strip it. Strip removes the symbols, makes the program a little smaller.